So today in this video we're talking about continuous charge distributions, meaning that, well, in the previous video we talked about discrete charge distributions, meaning that we had a finite number of charges that we can actually count, and but this time we're talking about a continuous amount of charges, meaning that there's a line of charge, a charge over a surface, or there's a charge over a volume. And basically, your little differential amount of charge is going to be equal to the charge density, rho sub L, times the little amount you move. This is for linear charges. The little amount you move along the line. So just like mass is equal to, well, density is equal to mass over volume. So mass is equal to the density times volume. But over a line, it's going to the density times the length. And that's exactly what's happening here. So dq is equal to density times the length. Integrate this, and you get this integral. Well, it's going to be 1 over the line. That's your total charge on the line. Now, for the electric field, we define the electric field to be Q over 4 pi. Well, get the epsilon out of the way. 0. And my 4 pi. 4 pi epsilon 0 all squared. Now, we have our Q, the expression right here. We just replace it with this and take the integral over the length, and this is our electric field due to a line of charge. Now it's important to know that this r squared will vary. It's not constant. It will vary as you evaluate the integral. Now, that being said, you can sort of extrapolate that into a surface integral, which are these expressions right here, and a volume integral. The logic is exactly the same, except you're integrating over a surface, therefore it's a double integral, and it's ds, and it's the surface charge density. Same thing with volume. Volume charge density, dv, triple integral for volume. Likewise, you can get all the electric fields the same way. Alright, we can get rid of that. Now, for this first example, we're going to be talking about a line charge distribution and the expression for the electric field of a line charge. And I'll do other videos on surface and volume charge, and then we'll realize later that there's actually an easier way to do it than this, but for now, this is what we're dealing with. Centered it. Looks kind of complicated, but I suggest that you pause or draw this, because I can't keep both on screen at the same time. I have to put one and the other. Basically, you have a point. Basically, all right. So this is our line of charge from A to B. Our dl is the way we're evaluating. It's going up, and the dl coordinates is 0, 0, z prime. Usually you put primes for source points, meaning the source of the electric field has primes, while the point we're interested in out here, some arbitrary point, has x, y, z. These are the vectors of the electric field. In the z and rho direction, we will be using polar coordinates. Alpha 2 and alpha 1 are the limits of integration. Basically, we're doing like an angle-based coordinate thing going on here. This is any intermediate r. This is any r that occurs in the integral, and that's its angle alpha. And alpha goes from 1 right here to 2. So this gets smaller, this distance right here, as it goes up to b. So that's the geometry we are working with. So let's start to just construct what our expression will be. Well, our dq, we said before, was rho sub L dl, but that's going to be equal to rho sub L dz prime, because the only direction we're changing is in the z prime direction, because remember I said prime is source points. These are the source points right here, the source of the electric field. So we're changing in the z prime direction. And so what we're doing here is we're getting each part of the integral. The next part we need to get is r, which is this vector right here. That's going to be, if you look at the geometry, as I said, you should write it down. It's going to be x, y, z minus 0, 0, z prime, and that translates into x, a sub x plus y, a sub y, plus z minus z prime, a sub z, or we're going to put this in polar coordinates. This expression right here is actually equal to rho a sub rho, because that's the polar coordinate expression for the rho unit vector. I will do a video on polar coordinates sometime in the future, if you don't know. So by this, that means that r squared is simply rho squared plus z minus z prime squared, and that means that the unit vector a sub r is going to be, well, this divided by the magnitude of that, which is just the square root. Well, actually, yeah, it would be this, because that is the vector. So it's actually equal to r over magnitude of r. Well, yeah, let's write it this way. It's a sub. We're looking for a sub r over r squared, because that's what's in our integral for electric field. Let me write the integral up here, just in case you've forgotten it. It's E equals over L rho sub L dl, and then 4 pi epsilon 0 r squared, and then we have a sub r. So right now we're trying to find a sub r over r squared, and that is it would actually be, I was getting a little ahead of myself. It would be this, but well, yeah. Okay, a sub r over r squared is equal to r over the magnitude of r cubed. That was in the previous video, and the magnitude of r squared is this. So that means that r equals the square root, and this is what I was doing before, so it's just this cubed, but that cubed is actually to the 3/2, like that. So now, if we replace everything in our integral, we have enough to replace. This is going to be, well, we can factor out the rho sub L because we're assuming that it's constant charge density. Factor out the 4 pi epsilon 0. And now we just replace everything with that, and it's dz prime. So that's what we're looking at. Now we need to make some substitutions in order to evaluate this integral. So that we go back to the geometry. You'll notice that z prime is actually equal to, I could close this one out. Yeah, it's actually equal to, let's write it down, z prime is actually equal to z minus rho tangent of alpha. And that's because z is this distance from the bottom to the top, and then rho tangent of alpha is this distance right here, because alpha is this angle. So we want to get to this point. So it's this distance minus this distance, so it's z minus rho tangent of alpha. and that means that dz prime is equal to negative rho secant squared of alpha d alpha. Okay, so we can actually substitute everything in now. That's pretty much all we need. This is going to be, well, z minus z prime. If we just replace z prime with this, we see the z's go out, and this actually turns to a plus, and distribute that. We'll put that square through, and you get this. Up here you get this same sort of thing. You get rho tangent of alpha because the z's go out again, and gotta replace dz, of course. We'll put that in parentheses. Why can't I highlight it? There we go. Put it in parentheses, and take this negative out. Put it out here. We will take a rho. This is going to be rho squared. And don't confuse these rows here. Rho sub L is the charge density, and rho is the radius for cylindrical coordinates. If you factor out a rho squared, this bottom part right here, if you factor out a rho squared, you get 1 plus tangent squared alpha. But 1 plus tangent squared is actually secant squared. Secant squared alpha, and then you take this, because it's 3/2, you take the square root and then you cube it, and that actually makes these cubed, and get rid of these brackets. Rho squared here cancels out with rho cubed here. You can pull this out. This cancels with the bottom, just making it secant, and you have d alpha. But 1 over secant is just cosine, so we're just going to multiply this numerator by cosine. Cosine of alpha, and then a tangent times cosine is sine of alpha. So we have this integral right here, and we just evaluate it. It's going to be, well, negative sine, well, no, sine of alpha, because the integral of cosine is sine, and then minus cosine of alpha. That's evaluated between, let's do this little bar here, alpha 1 to alpha 2. So that means E, the electric field of a, well, let's actually do it. It's going to be sine. We're going to distribute this negative through. Negative sine of alpha 2 minus sine of alpha 1, and then that's going to be plus because we distributed the negative. Cosine of alpha 2 minus cosine of cosine of alpha 1, and oh, we can't forget our unit vectors. Those got to get dragged along as well. Those are actually extremely important. Cannot forget them. And this is the expression for the electric field of a finite line charge. Now, if the line is infinite, that means B goes way up, A goes way down, and consequently, you get alpha 1 equal to pi over 2, and alpha 2 is equal to negative pi over 2. When you plug all that into here, you just plug in pi over 2 and negative pi over 2 for alpha 1 and alpha 2 respectively, and you get E equals almost the same kind of thing. It's going to be this, and it's going to be 2, and it's going to be 2 pi epsilon 0 over rho, and it's going to be in the rho direction only. So this is for a infinite line charge, this is for a finite line charge, and next video I'll be doing surface charge and then volume charge. So thanks for watching.